Welcome to Get Your FRQ On. This question comes from the 2009 B exam, and it's free response question number 6. It is not calculator active. In the question stem, we're given a table that represents values of time and the velocity of a particle in motion at different values of time. And we're also given an initial condition for the position of the particle when t is equal to 0, which we will use later in this question. In the first part of the question, we are asked to estimate the acceleration of the particle at time t equals 36. T equals 36 is not one of the values in the table, so we have to estimate it using the values that are in the table. And one of the expectations for a question like this on the AP exam is, since t equals 36 is not one of the values in the table, we need to estimate the acceleration at times t equals 36 using the two values in the table closest to t equals 36. That is the expectation in a free response question. I know there's many values in the table that you could use or combinations of those values to estimate the acceleration at time t equals 36, but the expectation is that you use the two closest. In this case, that would be t equals 32 and t equals 40. So based on the values in the table, the acceleration, which is the derivative of the velocity function at time t equals 36, we would estimate using v of 40 minus v of 32 over 40 minus 32. Importing values from the table, we get 7 minus negative 4 all over 8. And so the acceleration at time t equals 36 would be about 11/8 meters per second per second. In part B of the free response question, we are asked to use a trapezoid sum and explain the meaning of the definite integral from 20 to 40 of v of t dt. First, explaining the meaning of the integral. The integral from 20 to 40 of v of t dt would represent the net change in the position of that particle between t equals 20 and t equals 40. All right, this is basically an application of net change problems in calculus after the fundamental theorem of calculus. To actually calculate or estimate this integral, using trapezoid sum, we have to again go to the values in the table. So based on the table, using a trapezoid sum, we have to find the width of each interval and then take into account both endpoints, the function value at both endpoints on that interval. So the integral from 20 to 40 of v of t dt is going to be 5/2 times negative 10 plus negative 8 plus 7/2, which is the width of the second interval, negative 8 plus negative 4. I'm sorry, it's not the width of the second interval, it's the width times the 1/2, plus 4 times negative 4 plus 7. And if we simplify that, we get a total of negative 75 meters. So the particle has had a net change in position of negative 75 meters, indicating it's 75 meters to the left of where it began. All right, so between t equals 20 seconds and t equals 40 seconds, the particle's position changed by negative 75 meters. And remember, with questions like this, these are typically signed values. Negative 75 meters is interpreted to be motion to the left. Positive 75 would be motion to the right. So the negative 75 does have a very specific meaning. In part C, we are asked if the particle must change direction in any of the subintervals in the table, and if so, explain. If not, explain why not. So since we're given that v of t is differentiable on the interval from 0 to 40, it follows that v of t is continuous on the interval from 0 to 40. And from this, we can conclude that v of t is also continuous on the interval from 20 to 40. Right? The intermediate value theorem applies to v of t on this interval. Right? So it has to be continuous on the interval from 20 to 40. So, from the table, we just check the signs of the values of v of t. Right? We're basically looking for sign changes. It's an intermediate value theorem. The particle will change direction whenever it switches from positive to negative at a 0. Okay, great. From the table, v of 20 is negative, v of 8 is positive, so between 8 and 20, the particle has to change direction. We also notice that v of 32 is negative, v of 40 is positive, and since 0 is between those two values, we can conclude that the particle must also change direction between t equals 32 and t equals 40. All right, so we have two changes in direction for this particle. Based on the table, we can tell that the particle will change direction in the 8 to 20 subinterval and again in the 32 to 40 subinterval. In part D of this question, if we assume that the acceleration of the particle is always positive for values of t between 0 and 8, why must the position of the particle at t equals 8 be greater than 30? All right, so first of all, if a of t is positive on that interval, that means v of t is increasing on the interval from 0 to 8. Okay. So keeping in mind what that means is if we break apart the interval into any subinterval, the value of the function at the left endpoint will always be less than the value of the function at the right endpoint. All right, so the left endpoint represents a minimum on that subinterval. All right, so this would imply that the integral from 0 to 8 of v of t dt is greater than or equal to 8 times v of 0. Right? V of 0 is a worst case scenario. Right? And since v of 0 is 3, the definite integral from 0 to 8 of v of t dt must be greater than or equal to 24. Must be. Okay. The actual position of the particle at t equals 8 can be calculated using a definite integral. All right, so v of 8 can be found by taking v of 0 and adding to that the definite integral from 0 to 8 of v of t dt. Well, we're given in the question stem that v of 0 is 7, right? So 7 plus that integral, but that integral, remember, has a lower bound of 24. So v of 8 has to be greater than or equal to whatever 7 plus 24 is, which is 31. So v of 8 has to be greater than or equal to 31. Well, if that's the case, then clearly v of 8 has to be greater than 30 because it has to be greater than or equal to 31, and 31 is definitely greater than 30.